Hello, this is Drew Waltz, ISO Coordinator and Training Manager for Iris LLC, located in sunny Bradenton, Florida. Today I'd like to discuss the benefit of time signal versus FFT for slow speed bearing testing. Slow speed bearings have often been a source of frustration for facilities all over the world when trying to test with vibration analyzers. These slow speed bearings and mills can often be placed in hot, wet places, making it hazardous for the inspector to be exposed for a long period of time, not to mention the potential effects on the testing equipment. With vibration analyzers needing to test 3 points per end, this can take a lot of time to get a good reading, whereas ultrasound only needs as little as 15 seconds of sound recording to determine the condition of a slow speed bearing. When it comes to slow speed bearings, it's a lot like a rumble strip on a highway. If we hit the rumble strip at 55 miles per hour, it takes less time for the tire to traverse the depression and gives us a high-pitched sound versus hitting it at 5 miles per hour, where the tire takes longer to traverse the depression, giving it deeper, more distinguished thumping sound. Similarly, slow-speed bearing deformations of the surface will be more pronounced than in a higher-speed bearing. When it comes to slow-speed bearing analysis, one of the best ways to view these sound waves once captured is through the time signal analysis, also known as time waveform. This will give us a great amount of information as we can clearly see the occurrence of the deformations. Now I'm going to play a sound wave here for you to take a listen to. I'm now going to play another bearing. This is a 1 RPM kettle bearing from a foundry. So as we could clearly hear in that sound wave, there's definite damage that is indicated both in the time waveform and in the frequency spectrum. First off, however, I want to zoom in on this first little section here around 18,000 hertz that we've got going on here. Now, we see a tall harmonic indication that I'm going to mark real quick. And we're falling about 18,037. I also have these little side bands going on here, which I want to try to see if I can get a value on their harmonic interval. And if we start marking a couple other ones, we see we have a pretty repetitive pattern developing here in the FFT. If we take a look at our value now, let me shut off my marker. If we take a look at our value, we're roughly about 60 so hertz from 17,890 to 17,937. Then we come over here again, and now we're at like a 50 hertz interval. Then we come over here, and now we're at another 50 hertz interval. So we have some patterns that potentially could be showing up here. Now, if I line these up exactly, then we'd start to see a bit more linear matching here going on. But as we start to go down into the time waveform as well, we can move this cursor along here, and we'd see our amplitude change as well in our FFT and in our time signal below. So this top box here from 0 to 60 seconds is the entire time waveform. So we're looking at the entire clip. This smaller box lets me zoom in on a smaller section here, which I can also do the same. I can mark harmonic markings here as well. So we can start to determine what our frequency of occurrence is. And if we divide one by a frequency of a known harmonic occurrence, such as a ball pass, cage, inner race, or outer race, we can extrapolate what these values are down below in the time waveform as well. And again, sometimes we'll find more information in the time waveform when we start dealing with slow speed bearings than we do in the FFT. We can even take a look in different views here, and spectrogram will take these same values and compute it into an actual color overlay of amplitude and frequency of occurrence. And again, we can see this value here around 18,000 hertz and change that we'd marked earlier on the FFT. If I come over to my other screen, I can do a spectrum analysis where I can then take my harmonic marker and move it horizontally, and we find that our value is falling roughly around 18,000, and let's fine tune a little bit more here. 18,037 mark again. So we're matching up with our amplitude, that bright yellow line there. We also have my vertical lined up here with my highest amount of red that I see in the screen, which is right down here. So let's line our horizontal up again. And on the right side, we have a cross section basically representing what we see on the spectrogram, and down below we have our actual FFT. But my favorite screen to take a look at is spectrogram surfacing. This is the best of all worlds, FFT and time waveform analysis. It gives us the capability to see all the amplitude of occurrence in a 3D mapping with hertz, time, and amplitude and curve. So we can take a look here and we can clearly see that we've got some deviations here, deformations that would definitely be of concern. And again, we've got this nice big red spike here. We can zoom in on this, we can take a better look here, we can flip it upside down. Whichever way you want to look at this, I have a lot of capability to determine what's going on. Now, we're not able to mark any harmonic markings here, but this is a great way to report to somebody that, hey, look, we should have a smooth consistency with our spectrogram surfacing when we're looking for a good bearing. This spike of energy here, this spike of energy, we got a lot of peaking, we got a lot of amplitude that shows up in this ridge right here around 18,037. So being able to take a sound wave and look at a slow speed bearing, we can dissect it both in an FFT and a time waveform. And if you have 3D waterfall capability or 3D spectrogram surfacing, you can really get a great view of what's going on with your sound wave. You can then produce a report that makes you feel pretty confident in turning that over to somebody and letting them hear and see what's occurring. So I hope this was a little helpful tip. I hope you join us for some more upcoming training sessions in the near future.